Welcome back to the deep dive. Ever wondered how the digital world learns to recognize your messy handwriting or predict a fair price for a house? Or even what happens when the amount of data a machine needs to learn from is just, astronomically massive, so big it won't even fit into a single computer? Today, we're taking a deep dive, a shortcut to truly understanding some fundamental machine learning techniques and how they cleverly adapt to the very real world challenge of big data. Our mission today is to unpack the k-nearest neighbors algorithm, a surprisingly intuitive approach to both prediction and classification. And then, here's where it gets really interesting. We're going to explore the ingenious methods used in scikit-learn to handle data sets so immense they literally can't even fit into your computer's memory. We'll be drawing from several in-depth demonstrations, walking you through practical applications and the smart mechanics behind them. Think of it as a journey, from understanding how a single decision is made to how millions of decisions can be learned from a continuously flowing stream of information.
For this deep dive, we've got some fantastic demonstrations from the IIT Madras BS degree program. Our sources meticulously explore KNN for regression with the California housing dataset, then pivot to KNN for classification using the iconic MNIST handwritten digit dataset. We'll also ground ourselves with a foundational look at KNN's inner workings and its scikit-learn implementations. And finally, we'll immerse ourselves in large-scale machine learning, covering critical concepts like partial fit and incremental data processing. It's a comprehensive journey, really, from the elegant simplicity of the basics all the way to the advanced practicalities of applying these concepts in the wild, solving problems where scale is king.
Okay, let's unpack this fascinating world of machine learning. We're starting with k-nearest neighbors, or KNN. What exactly is this algorithm, and why is it often called instance-based learning? It sounds a bit like it doesn't really learn in the traditional sense, right?
That's a perceptive observation, actually, and it gets right to the heart of what makes KNN unique. At its core, KNN is what we call a non-generalizing, or, more commonly, an instance-based algorithm. This means it doesn't build an explicit, generalized model during its training phase, unlike many other machine learning algorithms. Think of something like linear regression, which learns a set of coefficients to define a line or plane. KNN doesn't do that. Instead, it simply stores all of the training data instances. This is why it's often called a lazy learner.
Lazy learner, huh? So it doesn't do much work up front.
Exactly. It doesn't put in much effort up front to build a model. It waits until it's asked to make a prediction. The real magic of KNN, and what makes it surprisingly powerful, despite its simplicity, is how it makes decisions. When it encounters a new, unseen data point that it needs to classify or predict, it looks at its neighbors, which are simply the data points in the training set that are closest to it in the feature space. Imagine you're at a party, right, and you meet someone new. You don't know anything about them, but you look around at the people they're standing closest to. If most of those people are, say, engineers, you might reasonably guess the new person is also an engineer. KNN operates on that same principle. Tell me who your closest friends are, and I'll tell you who you are.
Okay, that's a really clear analogy. So how does that translate to classification versus regression?
So for a classification task, the new point is assigned the class that is most common among its k-nearest neighbors. It's a simple majority vote. If you've chosen a k of 5, and 3 of those closest neighbors are labeled cat and 2 are labeled dog, the new point is classified as cat. It's, that's straightforward. For regression, where you're predicting a continuous value, it typically takes the average of the k-nearest neighbors' values. So if you're predicting a house price, and its 3 nearest neighbors sold for $500,000, $520,000, and $510,000, the prediction would simply be the average of those 3 prices. This adaptability allows it to capture incredibly complex, even sort of wiggly patterns in your data that other models, which try to simplify the world into rigid formulas, might struggle to represent. It truly lets the local data speak for itself.
So that lazy approach actually sounds quite adaptable then. How does sklearn, our go-to machine learning library, bring this concept to life? And are there different flavors of KNN that we should be aware of? Like, are there scenarios where one might be preferred over the other?
Absolutely. Sklearn provides 2 primary implementations for nearest neighbors, each suited for slightly different scenarios: neighbors classifier and radius neighbors classifier. The first one, neighbors classifier, is the one most people think of when they hear KNN. It operates based on a fixed number, k, of nearest neighbors. You explicitly tell it, always find me the 5 closest points, for example. The choice of k is a truly crucial hyperparameter here. It's highly data dependent, meaning you'll spend some time carefully tuning it to find the optimal value for your specific data set. A K that's too small can be sensitive to noise, while a K that's too large can smooth out important local patterns.
Okay, so neighbors classifier uses a fixed count. What about the other one, radius neighbors classifier?
Right. Radius neighbors classifier is a fascinating alternative. It's particularly useful in scenarios where your data might not be uniformly sampled, or if you have varying densities of data points across your space. Instead of a fixed K, this classifier considers all neighbors within a fixed radius R of the new data point. So if a new point happens to be in a very dense area of your data, it might naturally pick up many neighbors within that specified radius R. But if it's in a sparser, more isolated area, it will, by design, naturally use fewer nearest neighbors for its classification or regression, because there simply aren't as many points within that radius. The default radius value in Sklern is 1.0.
Ah, so it adapts to the density. That makes sense.
Exactly. This makes radius neighbors classifier more flexible for datasets where density varies, ensuring that predictions aren't overly influenced by distant points in sparse regions, which could otherwise skew the outcome. It allows the model to adapt to the local density of your data.
Okay, let's focus on neighbors classifier then. Seems like the main one. If we're going to primarily use that, what are the most crucial levers we can pull to make it work best for our specific data? What parameters do we absolutely need to know about to tune and optimize its performance?
You're right to focus on the key levers, as they can significantly impact performance. The most fundamental parameter, which we've already touched upon, is neighbors. This is your crucial K, the number of nearest neighbors to consider. The default value for this is 5. Choosing the right K is often the most significant tuning step, as it balances the bias-variance trade-off. Too small a K can lead to high variance, sensitivity to noise, while too large a K can lead to high bias, essentially over-smoothing and missing local patterns.
Got it. K is key. What else?
Next, we have weights, which determines how those K neighbors influence the final decision. By default, it's set to uniform. This means all points in the neighborhood contribute equally to the majority vote or average. However, you can set it to distance. This is a powerful option because it means closer neighbors have a greater influence, weighted by the inverse of their distance.
Why would we want to do that? Why weight by distance?
Well, it's about giving more importance to the truly nearest points, which are often more representative of the local data distribution. Those points are likely to be more similar, right? So their input should inherently carry more weight. You can even go a step further and define your own user-defined function for weights, which offers incredible flexibility if you have specific domain knowledge about how closeness should translate to influence in your particular problem.
Interesting. So, K, weights. What else controls how it works?
Then there's the algorithm parameter. This addresses the often computationally expensive part, how the algorithm efficiently finds those nearest neighbors. For smaller data sets, a brute force search checking every single point might be okay. But for larger data sets, it becomes incredibly inefficient. That's where tree-based data structures come in. Ball tree or AD tree. These are clever ways of organizing your data so that finding the closest points is much faster, like using a very efficient indexing system in a library instead of just scanning every single book. The default is auto, where Sklern attempts to select the most appropriate algorithm based on your data's characteristics, typically choosing a tree-based method, if it makes sense.
Okay, trees for speed. Anything else major?
Well, related to the tree algorithms, you have leaf size. This parameter, default 30, affects the speed of tree construction and querying, and also the memory required to store the tree. It's more of a fine-tuning parameter for performance. And finally, we have metric and P. The metric defines how distance or closeness is actually calculated between data points. The default is Minkowski with P2.
Which is just standard Euclidean distance, right? Like a straight line.
Exactly, that straight line distance we typically think of. But you have other options like Manhattan city block distance, like navigating city streets, or Chebyshev. Understanding the choice of metric is essential because it directly impacts how closeness is defined for your data. Different types of data might benefit from different ways of measuring distance, and a poor choice can dramatically affect which points are considered neighbors.
That's a fantastic deep dive into the KNN mechanics. Now, let's ground this theory with a concrete, real-world example. We're going to talk about predicting house prices in California using the well-known California housing dataset. What does this dataset look like, and how do we prepare it to apply KNN?
Right. The California housing dataset is a classic choice for demonstrating regression problems, and it's a robust, real-world example. It contains 20,640 individual examples, with each example representing a block group of houses in California. Each block group is defined by 8 distinct features, things like the median income of the residents in that block, the average number of rooms per dwelling, average bedrooms, population, average house occupancy, and geographic coordinates like latitude and longitude. The target variable, what we're trying to predict, is the median house price for that specific block. We load this data using Fetch California Housing and crucially set return XE, true, which conveniently gives us separate feature matrix X and label vector
Right,
1.
and then you split it. Right, training and testing.
Absolutely. After loading, a standard and absolutely crucial step for any machine learning task is data splitting. We divide the data set into a training set, which is 70% of the data amounting to 14,448 examples, and a test set, the remaining 30%, or 6,192 examples. This split is critical for evaluating your model's true performance on unseen data. You train the model only on the training set, and then you test its ability to generalize by making predictions on the test set, which it has never encountered during training. This ensures your model isn't just memorizing.
Before we even think about building the KNN model, we heard about feature scaling. This seems particularly important for KNN, especially when you have features like median income, which might be in the tens of thousands, and average rooms, maybe single digits. Why is scaling so critical here?
You've hit on a core reason why scaling is paramount for distance-based algorithms like KNN. What's crucial here is that features in this California housing dataset, as you rightly point out, are on very different scales. Since KNN uses distance metrics like Euclidean distance to find neighbors, a feature with a much wider range or higher variance would completely dominate the distance calculation. Imagine a difference of $20,000 in median income versus a difference of just 2 rooms. The $20,000 difference would create a massive distance component that would utterly swamp any contribution from the average rooms feature, essentially making other features almost irrelevant.
Right, it's like judging similarity based only on income and ignoring everything else.
Exactly. The solution is to use min-max scalar. This transformer brings all features onto the same scale, typically between 0 and 1. By doing this, we ensure that all features contribute proportionally to the distance calculation. No single feature, simply because of its larger numerical values, can disproportionately influence which points are considered nearest. It's a fundamental pre-processing step for any algorithm that relies on calculating distances. Without scaling, your KNN model would likely make very poor predictions.
Okay, so the data is prepared and scaled. Now, how do we put KNN to work for predicting these house prices? What does the initial model setup look like, and how do we measure its performance?
With our data prepped, we construct a pipeline object. This is a powerful feature in Sklearn that lets you chain together multiple processing steps and a final estimator. Our pipeline has 2 stages. First, the min-max scalar for scaling, and second, the neighbors regressor itself. For our initial model, just for demonstration, we arbitrarily set the number of neighbors, k to 2. This means the predicted price of a new house would simply be determined by the average price of its 2 nearest neighbors in the scaled feature space. It's a very small neighborhood, which can sometimes make predictions a bit volatile.
And how did that initial K2 model do?
Once this pipeline is defined, the model is trained by calling fit on our scaled training data. After training, it's evaluated on the unseen test set using the mean squared error MSE metric. For this initial setup with K2, our demonstration yielded an MSE of 0.67. Now, to give you a sense of what that means, if you take the square root to get the root mean squared error, or RMSE, which is in the same units as our house prices for this normalized data, an RMSE related to 0.67 indicates an average prediction error. So our model's predictions, on average, were missing the actual house price by a certain amount. This gives us a baseline.
An MSE of 0.67 sounds like a start, but we know xk is a crucial hyperparameter. How do we find the best k to genuinely optimize our predictions and get the most out of our model? Are there systematic ways to do this?
This raises a critical question in machine learning. How do we optimize the model? Our sources demonstrate 2 main approaches for tuning k. The first is manual hyperparameter tuning with cross-validation. Here, we set up a loop to iterate through a range of k values, perhaps from 1 to 31. For each k value, we build and train our pipeline that make predictions on the test set and calculate the root mean squared error, or RMSE. The RMSE is often preferred over MSE for interpretability, as it's in the same units as the target variable.
And what does that typically look like when you plot RMSE against k?
If you were to plot k on the x-axis and RMSE on the y-axis, you'd observe a very typical learning curve for KNN. The RMSE initially drops sharply. This indicates that increasing k from a very small number helps smooth out predictions and reduce sensitivity to noise. However, after a certain point, the RMSE starts to go up again. This signifies that choosing too many neighbors can lead to oversmoothing or introducing bias, where the model starts to include points that are too far away. The point of lowest RMSE on that curve suggests the optimal K. In this specific California housing example, the lowest RMSE was found at K9.
Okay, so manual looping works, but sounds tedious. What's the automated way?
The second approach, and often the more practical and powerful one, is automated tuning with Grid Search CV. This tool automates the process. You define a parameter grid of K values you're interested in, again 1 to 31 in our example. You then instantiate Grid Search CV with your neighbor's regressor, or your pipeline, your parameter grid, and specify the number of cross-validation folds, like 10-fold cross-validation. The fit method on Grid Search CV then systematically trains and evaluates the model for all K values in the grid across all specified folds. It's like having a meticulous assistant try every single combination for you.
And did Grid Search CV find the same optimal K?
Interestingly, no. After the grid search completes, the best estimator attribute reveals the optimal K. For this dataset, Grid Search CV found the best K to be 6, which resulted in an RMSE of 0.62. This wasn't just a win for automation. It highlights that sometimes the optimal solution isn't intuitive. Grid Search CV's systematic approach often uncovers nuances that manual tuning might miss, leading to genuinely better performance. This is a noticeable improvement over our initial K2, and even better than the RMSE at the manually found K9. The sources also mention Randomized Search CV as another automated alternative, which is particularly useful for larger parameter spaces where you maybe can't check every single combination.
That's great for finding the best K, but what if the relationship between our features and the house price isn't just a simple linear one? What if it's curved or more complex? Can K&N handle these more intricate patterns, and how would we go about exploring that?
That's an excellent question, and yes, we can absolutely enhance the model to potentially capture nonlinear relationships by incorporating polynomial features. This is a very clever pre-processing step. Instead of just using your original features, polynomial features transforms them into polynomial combinations. For example, if you had median income and average rooms, it could create new features like median income squared, average rooms squared, and even an interaction term like median income multiplied by average rooms. This could be incredibly powerful if the underlying data truly has curved or synergistic relationships that basic K&N might struggle with.
So you'd put that into the pipeline before scaling.
Exactly. We set up a new pipeline. First, polynomial features to create those new terms, then min-max scaler for scaling, and finally, our neighbor's regressor. The beauty of the pipeline is that we can then use Grid Search CV again to perform a joint hyperparameter search. In this demonstration, we searched for the best degree for polynomial features, from 1 to 4, and the best K for K&N, from 6 to 12, simultaneously. This lets us find the optimal combination of complexity and neighborhood size.
And what was the result? Did adding polynomial features help?
The results of this joint grid search were quite telling. It found the optimal polynomial degree to be 1.
Degree 1, so
Yeah.
just the original features.
Precisely. It means that for this specific California housing dataset, a simple linear transformation, essentially just the original features themselves, was actually sufficient and best, along with an optimal K of 6. The resulting RMSE remained comparable at 0.62. This outcome is a powerful reminder. More complex doesn't always mean better. While polynomial features are a fantastic tool, for this dataset, simpler transformations coupled with an optimally tuned K worked perfectly well. It's a classic example of Occam's razor in machine learning. The simplest effective model is often the best.
All right, that's a brilliant deep dive into regression with K&N. Now let's pivot to a completely different kind of data and problem, from predicting house prices to recognizing handwritten digits. We're talking about the famous MNIST dataset now. What's the core challenge here with MNIST, and why is it such a benchmark in classification?
MNIST. It's practically a rite of passage of machine learning, specifically for handwritten digit recognition. It's a massive collection of grayscale images of handwritten digits from 0 to 9. Each individual data point, each image is represented by 784 numbers. These numbers correspond to the pixel values of a 28 by 28 pixel image. Think about it. A small square image, and each tiny square within it has a number representing how dark or light it is. And of course, there are 10 possible labels, the digits 0 through 9. The inherent challenge lies in accurately classifying these visually similar yet distinct handwritten forms into their correct numerical categories, especially given the wide variation in human handwriting. It's a classic multi-classification problem.
784 features per image.
Wow, that sounds like an enormous amount of information, a real high-dimensional problem. Is there a way to simplify that without losing too much important detail, especially for something like image recognition, where details seem crucial? That's a perceptive concern, and it's a very common challenge. What's crucial here is how we can use principal component analysis, or PCA, to tackle this high dimensionality.
Yeah.
When you're dealing with 784 dimensions, it's not only computationally intensive for distance calculations in KNN, but it's also virtually impossible for humans to visualize. PCA allows us to transform these 784 dimensions into a much smaller set of principal components that capture the most significant variance or spread in the data. It's like distilling a giant map down to the most important landmarks. We can reduce them down to just 2 or 3 components for visualization, for instance.
So you'd run a PCA after scaling?
Yes. Typically, we create a pipeline of min-max scaler followed by PCA. Scale the pixel values first, then apply PCA to find the most significant underlying dimensions. Plotting these principal components, especially in 2D or 3D, gives us valuable visual insight. You can see that there's some separation between digit classes. Zeros might cluster somewhat separately from non-zeros, but there's also significant overlap. This overlap highlights the inherent complexity. It's important insight because visualization in lower dimensions gives a rough idea, but might not capture all the nuances the full 784 features contain.
Let's start with a simpler problem then. Instead of recognizing all 10 digits, can KNN just tell us if a digit is a 0 or not? A binary classification task. How does that initial setup look?
Absolutely. For a binary problem, like 0 versus not 0, we simply relabel the data. 0 becomes class 1, and all other digits 1 through 9 become class 0. This simplifies the problem dramatically.
And how did that work in the demos?
Our sources first showed this with a tiny demo, which is great for intuition. Using Neighbors classifier with KE3 on just 10 training and 10 test samples, we saw 5 out of 10 test points misclassified. A confusion matrix helps visualize this. What's particularly cool about KNN here is you can print the distances to the 3 nearest neighbors and their labels for each test point. It helps you understand why a prediction was made. You see which training examples influenced it.
Okay, that's tiny. What about scaling up, maybe with PCA?
Right. Scaling up, we then applied this to 10,000 training samples using the min-max scaler plus PCA with 2 components, plus Neighbors classifier pipeline. The classification report for detecting 0 class 1 showed a precision of 0.65, recall of 0.63, and an F1 score of 0.64.
Remind us quickly what precision and recall mean here.
Sure. Precision asks, out of all we predicted were 0, how many actually were 0? Recall asks. Out of all that actually were 0, how many did we find? The F1 score balances them. These scores indicate moderate performance with dimensionality reduction.
And did tuning K help much in that PCA scenario?
We varied K from 1 to 19 and plotted precision. We observed it hovering consistently around 0.65, suggesting that with PCA reducing to just 2 components, performance plateaued. This might mean the reduction itself was losing too much critical information.
That's a great point about the trade-offs. So if PCA might be limiting performance, what happens if we bite the bullet and use all the original 784 features? Will that give us better results even if it's more computationally intensive? Is it always worth it?
This raises that important trade-off question again, computational cost versus model performance. While using all features increases the computation for distance calculations 784 dimensions versus 2 or 3, it often, as you suspect, significantly improves accuracy, especially in rich datasets like images where every pixel can carry crucial info. It's not always worth it if the cost is prohibitive, but in cases like image recognition, the detail often outweighs the added computation.
So how did you find the best K using all features? Back to Grid Search CV.
Exactly. We again turned to Grid Search CV. We set up a simpler pipeline, just min-max scaler, followed by Neighbors classifier, no PCA this time. We searched for K values, 1, 3, 5, 7, 9, 11, using 5-fold cross-validation, scoring by precision. We also used Algorithm Auto and Ngjob's Mass Demanded 1 to use all CPU cores, speeding things up given the higher dimensionality.
That was the better.
It was significant.
Okay.
The best K found was 7. Evaluating this model on the test set without PCA resulted in only 35 misclassified examples out of the test set used. This is a dramatic improvement over the moderate performance with PCA. This highlights that for MNAST, preserving all original features was more beneficial than dimensionality reduction with PCA, despite the computational load. It really shows sometimes simpler models with richer data can outperform complex pipelines that might discard valuable info.
So we've successfully classified a single digit using all features. Now for the full challenge, extending KNN to a multi-class problem to recognize all 10 digits, 0 through 9. Is it just a straightforward extension, or are there new complexities?
Indeed, extending KNN to multi-class problems like this is quite straightforward conceptually. The underlying logic naturally handles multiple classes. When predicting for a new point, it still finds its k nearest neighbors, and then instead of a binary vote, it performs a majority vote among all possible classes present in those neighbors. The new point gets assigned the class with the most votes. So we simply apply the same min-max scalar plus neighbors classifier pipeline with our optimally found k is 7 to the full MNIST dataset with all 10 original labels.
And how did that perform, the full multi-class problem?
What's remarkable is the performance. The confusion matrix shows much fewer confusions compared to the binary case, most predictions falling squarely on the diagonal correct classifications. When we look at the classification report, it reveals F1 scores greater than 0.95 for all digits, which is truly excellent. The highest were 0.98 for digits 0, piece, and 6n. The overall accuracy achieved was a very compelling 97%, with macro average, precision, recall, and F1 scores all also at 0.97. This clearly demonstrates KNN's effectiveness on this real-world task when properly tuned and given sufficient rich features. It really shines when patterns are distinct, even if high-dimensional.
That's incredible performance for such an intuitive algorithm. But now let's zoom out to one of the biggest challenges in modern machine learning. We've seen how powerful these techniques can be, but often, especially in the real world, the data is just too big. What does large-scale machine learning really mean, and why is it such a significant problem for traditional approaches?
You're touching on the defining challenge of our era in data science. In today's world, companies are collecting an explosion of data from customer interactions, industrial processes, IoT devices, social media, you name it. Large-scale machine learning means dealing with amounts of data sheer file size, number of samples, features, or classes that simply cannot fit into your computer's RAM all at once. This is what we call out-of-core data.
Like trying to fit an elephant into a smart car.
Exactly. It's just not going to happen. The problem is traditional fit methods in most ML libraries assume the entire dataset is loaded into memory. If it can't be, these methods fail, crash, or just won't run. Plus, consider scenarios where new data arrives continuously, like fraud detection or recommendation engines. Retraining the whole model from scratch every time new data comes in would be computationally prohibitive and incredibly inefficient. You need strategies for this out-of-core data.
So if we literally can't load everything into memory at once to train a model, how on earth do we actually do it? What's the clever solution Sklearn provides?
This is where the partial fit method in Sklearn becomes our absolute best friend. It's the central idea behind incremental learning or out-of-core learning. Instead of trying to load all the data, partial fit allows the model to process data in batches or chunks. Batches, like small pieces at a time. Precisely. Here's how it works. You load just one manageable batch into memory, use that batch to update the model's parameters and learn a bit, then discard that batch, load the next one, and repeat. The model continuously updates its internal state and learns incrementally as each new batch is processed until all the data, even terabytes, has been seen sequentially. It's like teaching a child with flashcards one at a time. This is essential for out-of-memory datasets and also for situations where new data arrives over time. Instead of retraining from scratch, you just update your existing model.
Okay, that sounds powerful. Any catches or things to keep in mind with partial fit?
Well, it does have some minor performance overhead compared to seeing all data at once. So it's generally recommended to use reasonably large batches, not tiny ones, for efficiency. One crucial input, particularly for classification, is that when you call partial fit for the very first time, it's highly recommended to supply the list of classes. This tells the model all possible outcomes up front, even if some classes are missing from the initial chunk. Otherwise, it might not recognize a new class later.
That makes a lot of sense for huge data sets, but is partial fit available for all Sklearn models, or is it specific to certain types of algorithms built for this?
That's an excellent question. And no, not all Sklearn estimators support partial fit. It's typically implemented by algorithms that can intrinsically update their parameters incrementally without needing to reevaluate the entire dataset each time.
So which ones do support it?
For classification, key ones include multinomial naive Bayes, Bernoulli naive Bayes, great for text, SGD classifier, stochastic gradient descent classifier, and perceptron. For regression, SGD regressor is the counterpart. And for clustering, mini-batch k-means implements partial fit.
SGD seems to pop up a lot here. Why is that particularly suited?
Right. The SGD classifier and SGD regressor are particularly well suited. Algorithms using full batch gradient descent usually need all data at once. In contrast, stochastic gradient descent, SGD, inherently updates model parameters using either single examples or small mini-batches. This chunk-by-chunk update mechanism aligns perfectly with partial fit, letting them deal with massive datasets effectively by processing sequentially. Load a chunk, update, move on. That's why SGD is a go-to for incremental learning.
That's a great conceptual overview. Let's see partial fit in action then. How does it compare to the traditional fit method when we actually run it on some data, and what are the trade-offs we might observe in practice?
We could demonstrate this with a synthetic dataset, say 50,000 samples, 10 features, 3 classes. First, the baseline. Training an SGD classifier, maybe max it or 1000, 12.801. Using the standard fit method yields a test accuracy and F1 scores around 0.87. That's our benchmark if everything fits in memory.
Okay, 0.87 accuracy with fit. Now, how do you simulate the out-of-core scenario?
To simulate out-of-core learning with partial fit, we pretend those 50,000 samples are too large. We save the training data to a CSV file. Then we read this file chunk by chunk using pandas.read CSV, specifying a chunk size, maybe 1,000 rows at a time. So we only load 1,000 rows into RAM at any moment.
Like reading a giant book one chapter at a time.
Exactly. For each loaded chunk, we then call partial fit on our SGD classifier instance. And remember, crucial step, provide the list of classes with the very first partial fit call. As we process each chunk, you can actually observe the model's coefficients and intercepts changing. It visibly shows the incremental updates happening as the model learns from the incoming stream.
So it's learning piece by piece. How did the final performance compare to the fit version?
After training with partial fit across all chunks, we evaluate on the same test set. In this demonstration, the test accuracy was slightly lower at 0.82, with F1 scores also marginally lower. Here's 0.88, 0.77, 0.83 across classes. This slight drop is a known trade-off. Because the model doesn't see all data at once, it might not find the absolute optimal solution. It's like mapping a city. Seeing one block at a time, you get a good map. Maybe not the perfect one. But this clearly shows how to use partial fit for large datasets when memory constraints make fit impossible. The flight performance hit is often a perfectly acceptable price for being able to train on massive datasets at all.
That's a great example. Now, shifting gears slightly, when we're working with text data, like analyzing customer reviews or articles, it's not numerical to start with, right? How do we prepare that for a machine learning model, especially when the text corpus itself is massive?
You're absolutely right. Text data isn't directly usable. It needs to be converted into a numerical vector representation. This process is called text vectorization. It transforms unstructured human language into structured numerical features an algorithm can understand.
So are there different ways to vectorize text, and how do they handle very large text data sets where memory is a concern, tying back to what we just learned?
Yes, and this is where hashing vectorizer becomes another crucial tool alongside partial fit for large-scale learning. Let's contrast it with a more traditional method, count vectorizer.
Okay, count vectorizer. How does that work, and what's the issue with scale?
Count vectorizer works by building a vocabulary from all unique words across all your documents. It then counts word occurrences in each document, creating a bag of words. The problem is, it stores this entire vocabulary in memory. For very large text corpora, millions of posts or articles, this vocabulary can have millions of unique words, quickly becoming too large for RAM. Even though its output is often a sparse matrix, saving space, the vocabulary itself, defining the columns, is kept in memory. In our small demo with 4 snippets, it found 66 unique tokens and stored them. This reliance on an in-memory vocabulary makes it less ideal for massive streaming text. So count vectorizer needs to remember all the words. How does hashing vectorizer avoid that? In contrast, hashing vectorizer is specifically designed for large-scale text. The key difference is it does not store a vocabulary. Instead, each token, word, is directly mapped to a predefined column position in the output matrix using a deterministic hashing function. You specify the desired number of output features with the end features parameter, say 50,000 or 100,000. This parameter is crucial. Too small causes hash collisions, where different words map to the same column, polluting the representation. Too large creates too many dimensions.
New vocabulary stores, so it uses much less memory.
Exactly. Significantly less memory. This also means it's stateless between chunks. It doesn't depend on seeing previous data, making it perfect for incremental learning and streaming data. The trade-off is interpretability. While it's memory efficient, you lose the easy ability to map back from feature IDs to actual words, unlike count vectorizer. You can't easily inspect which word corresponds to which feature column. It's a trade-off. Interpretability for scale.
That's a brilliant solution for text. So how do we combine this incremental data loading with text pre-processing using hashing vectorizer and then actual model training with partial fit? Can we see a full example of this powerful combination?
Absolutely. We can demonstrate this with a classic sentiment analysis task, classifying text documents as either positive 1 or negative 0. We'll use a dataset from the UCI machine learning library containing product reviews and their sentiment labels. Imagine trying to classify millions of product reviews streaming in real time. This is exactly the kind of setup you'd need.
And what does the complete incremental pipeline look like for the sentiment analysis task, linking the text vectorization with the model for continuous learning?
For this full incremental pipeline, we use hashing vectorizer for the incremental text vectorization. This is coupled with an SGD classifier. We configure the SGD classifier with a hinge loss function. The hinge loss essentially makes the SGD classifier behave like a linear support vector machine, SVM, aiming to find a clear, wide margin between the positive and negative classes. This combination is well suited for streaming text. Hashing vectorizer handles text efficiently without storing a vocabulary, and SGD classifier updates incrementally using partial fit.
This is where it all truly comes together. How does partial fit really help us train the sentiment model on data that arrives in chunks? Walk us through the step-by-step process.
Let's walk through it. Even though our example training set has 799 examples, which isn't huge, we'll pretend we only have limited memory to demonstrate the principle. So first training round, we take the initial 400 samples. We transform these text documents into numerical vectors using our hashing vectorizer. Remember, it's stateless, processes each snippet independently. Then we call SGD classifier.partialFit on these transformed samples and their labels. Crucially, this first call includes the list of classes, 0 and 1 for sentiment. After this initial partial training, we evaluate this model on our test set. Our initial accuracy score was 0.70. This simulates training with a first batch of available data.
Okay, 70% accuracy after the first 400 samples. What happens next?
For the second training round, we then process the remaining 399 samples. We again transform them using the same hashing vectorizer. As discussed, it doesn't store state, perfect for this. Then we call SGD classifier.partialFit again with this new batch. The SGD classifier takes what it learned from the first 400 and incrementally updates its parameters based on these new 399 samples. It's refining its understanding with each new piece of info.
And did the accuracy improve after seeing the rest of the data?
Yes. What's truly exciting is the improved performance. When we evaluate the model on the test set again after this second round, the accuracy score increases significantly, from 0.70 to 0.76. This clearly illustrates that partial fit allows the model to learn and improve over time as new data becomes available without needing to retrain from scratch. It's incredibly useful in real-world scenarios with continuous data streams, enabling models to adapt and get better over time without massive computational overhead. It turns a seemingly impossible problem into a dynamic solution.
So, what does all of this mean for you, our listener? Today, we've unpacked the elegant simplicity of K-nearest neighbors, seeing how its intuitive, lazy learning applies to both predicting house prices and classifying handwritten digits. We then zoomed out to tackle one of the biggest challenges in modern machine learning, how to learn from data sets that simply won't fit into memory. We introduced you to the power of partial fit for incremental learning and the clever hashing vectorizer for efficient text preprocessing. We've seen how these tools transform the seemingly impossible into the practical.
And if we connect this to the bigger picture, the ability to train models incrementally opens up truly exciting possibilities. Think about systems that need to constantly adapt a spam filter, learning from new emails in real time, a recommendation engine updating as your preferences change minute by minute, or even diagnostic tools learning from continuously arriving patient data. This raises an important question for you to ponder. How else might incremental learning transform the way we interact with intelligent systems in this world overflowing with data? What new applications could this enable in fields we haven't even imagined yet, moving beyond static models to dynamic, ever-evolving AI?
We hope this deep dive gave you some serious aha moments and equipped you with a clearer understanding of these powerful machine learning tools. Until next time, keep exploring, keep questioning, and keep learning.